Welcome to this lecture series in real analysis. We are starting a new module which will be about sequence of functions, and this module and the next will be in part devoted to building exponential and logarithmic functions. So far, our toolbox of functions or our repertoire of functions is rather limited. All we know is polynomial functions, ratios of two polynomials, and surds. That's pretty much all we know right now. And combinations of them, we can compose those and whatnot. But that's not a lot, that's not a lot of interesting functions. We would like to understand things like the exponential functions, which I'm sure we are familiar with from our high school and from physics, the logarithmic function, and of course also the trigonometric functions. So trigonometric functions will take even more time to build. But this, by the end of the next module, not this, but by the end of the next module, we will have finished our discussion on exponential and logarithmic functions, and also I would like to discuss some applications there. All right. So let's start with some basic definitions. Today's lecture will be particularly simple but very important. So suppose we have a subset of real numbers, then a sequence of functions on S. A sequence of functions on S is defined as, exactly as the name suggests, is a sequence. Let me write it this way, is a sequence where each Fn is a function from S to the reals. So, well, when I say sequence of functions, it could have been valued in any set. But here, perhaps I should have said sequence of real valued functions. But since we'll only be focusing on real valued functions, we do not need to qualify this. So when I say sequence of functions, until otherwise or unless otherwise mentioned, we will assume that all our functions are real valued. This is a course in real analysis after all. Okay, fine. So that's what a sequence of functions is. Here we defined it only for subsets of real numbers, the domain being a subset of real numbers, but that could have been, again, any set. However, we will only be interested in the domain being a subset of reals. Okay, unclear why this concept is coming about, but it's actually a very natural concept. But before we get into any more theory, let's at least see or try to build some intuition via this very simple picture. All we are doing is, suppose the set S is this interval, then all we are doing is we are just plotting the graph of each of the functions here. In this picture, the functions look continuous, but there is no such assumption. The functions could very well be discontinuous. But when you are drawing a figure, it's just easier to draw a continuous function. So all we are doing is just plotting the graph of each function in this list, and the figure that we obtain will be something like this. Okay, so very simple concept. Now for something interesting and important. Suppose we are given a sequence of functions. So we have a subset of reals. For each n, we have a function with us. So we get a sequence of functions on S. We say this sequence converges pointwise if, I'll write down the formal definition, but first let's look at the picture. So again, this is the same picture. Again, all my functions look continuous, but they don't have to be. So as soon as you fix a point in the domain, if you fix a point in the domain, maybe I'll use a dark pen. Suppose we fix a point here, call it x0. Then each function in this sequence furnishes a real number. Right? So all I'm saying is that as soon as you fix something in the domain, we get this sequence of real numbers. Right? x0 is a fixed point in the domain, meaning in S. So this is a sequence. And we can ask if this sequence converges or not. So we say that the given sequence of functions converges pointwise if if for all points in the domain, the sequence of real numbers converges. As simple as that. If for each point in the domain, the sequence of real numbers furnished by the given sequence of functions converges, we call the given sequence of functions a pointwise convergent sequence of functions. That's it. Okay. Now, for an obvious follow-up definition, fix a subset of reals, fix a pointwise convergent sequence of functions on that set. We can define a new function. We define the limiting function or the limit function, f as fx is just the limit of the sequence obtained by restricting these functions to the point x. So, well, this is the way to write it. Right? So, since this sequence, as n grows from 1 to infinity, this is a convergent sequence by hypothesis. This is a meaningful real number, and we can obtain such a real number for each x, again by hypothesis, and therefore we can obtain a function, a bona fide function on the domain, and that is what we call the limit function. Automatic, very, very simple, natural definition, and we may express this by writing notationally. We may write like this. We may just say that, or we may write, to be more precise, pointwise. Or we may also write f as limit n going to infinity fn. That's also a perfectly fine notation. Okay. So now let's look at some examples. So here our set S is the unit interval, and we are defining the functions via their graphs. So the first function, you grow linearly from 0 to 1 up until the point half, and then you become constant equal to 1. So here I should have mentioned that this value is 1, but I don't want to clutter the figure. The function f2, what does it do? It grows linearly from 0 to 1 by 3. So the starting value is 0, the ending value is 1 again, and then it becomes constant. The function f3 rises even faster, but only up till 1 by 4, and then becomes constant. So the general description is fn of x is, well, I don't want to, okay. So this is equal to n plus 1 x if x is in this region, and 1 if this is the case. So you can see if n were equal to 1, this becomes f1, and what we are saying is that f1 is 2x, f1 of x is 2x if x is between 0 and half, and that's exactly what is going on. Okay, but the point is, what is the limiting function, or is it a pointwise convergent sequence of functions? You pick any point in the domain. So basically, I wanted to draw a vertical line, so this is a fairly good vertical line. So you fix any point, this point, and the value here, as we can see, is 1 all the way. At least visibly it is 1, because we are in this region, greater than half region. All the functions in this sequence will take the value 1. So it is clear that if you choose a point x which is greater than half, all the functions furnish the value 1 there, and therefore the limiting value for that particular So here, basically, we can just draw this horizontal line. I'm just trying to draw the graph of the limiting function if the limiting function exists. We, as of now, don't know if this is a pointwise convergent sequence of functions. We are trying to argue that it is. Okay, what if we had chosen a point somewhere here? Let's say somewhere between 1/3 and half, somewhere here. So the first function doesn't give us a value 1, right? I mean, if you choose a point here, then the first function doesn't give us the value 1, but the second function gives us the value 1. The third function gives us the value 1, and all the other functions also give us the value 1. So even there, the limiting thing would be 1. And you can reason this out for any x in this entire closed interval except the point 0. At the point 0, all the functions furnish the value 0. So at the point 0, the limit exists, but the limit is 0. Everywhere else it is 1. So the limiting function looks something like this. At 0, the value is 0, but at all the points greater than 0, the limiting value is 1. So this sequence of functions is pointwise convergent. But the limiting function is somewhat ill-behaved in the sense that it is not continuous. It takes a sudden jump. Each of these functions were continuous, clearly. Right? Each of these functions is continuous. They are also a pointwise convergent sequence of functions. But the limiting function is not a continuous function. So what we are seeing is that in the limit, desirable properties may not be conserved. Continuity is a very, very desirable property for a function to have. But in the limit, that property can die down. That property can go away, as we are seeing. Let's see one more example. This time we are defining fn. This is the unit interval, so same as that. So we are defining fn as x to the power n. Right? Is it a pointwise convergent sequence of functions? It is, and maybe first I'll suggestively draw graphs of these functions. So roughly it looks like this. I mean, f of 1 would be just this linear function. This is f of 1. Then f of 2 would be the squared function. F of 3 would be the cubed function. And so on. And note that fn of 1 is 1 for all n. Right? So at least for x equals 1, this sequence is a convergent sequence. But for any other x, if x is less than 1, then fnx by definition is x to the power n, and this goes to 0 as n goes to infinity. Right? And therefore, the limit exists. But what is the limiting function? The limiting function is little ill-behaved again. It is the constant function 0, except at 1 it takes a value 1. So here we have a similar situation. Each of these functions are continuous. In fact, they are polynomial functions. Polynomial functions are the best kind of functions. Still, the limit is not a continuous function. So pointwise convergence is a weak notion. We would like nice properties to carry over in the limit, but this notion of pointwise convergence seems to be pretty weak. And as we'll see in the next lecture and so on, that we have a more demanding notion of convergence for a sequence of functions, which does preserve many of the desirable properties, sometimes with mild hypothesis. Okay. So what is the source of this pathology? Why is it, or can we nail down some technical reason for the lack of carryover of continuity in the limit? So fix a sequence of continuous functions. Here I'm indexing them by k rather than by n. Okay, so we fix a sequence of continuous functions, and let us try to examine what can go wrong in trying to argue that the limit function is continuous. I mean, we are assuming that this is a pointwise convergent family, so assume this is a pointwise convergent sequence of functions. And let's try to argue that the limiting function is continuous. We know we cannot argue that, but we are trying to just nail down where does it go wrong. So let f be the limit function. Okay, what is the obstruction to the continuity of f? So suppose we wanted to show that f is continuous at a point x. So let x be fixed in S. We want to argue the continuity of f at x. So fix some sequence, fix a sequence xn in S such that xn converges to x. And we want to show that, or maybe I'll write it this way, want to show that, we know we cannot show it, but still show that, want to show that this is the case. That would prove the continuity of f at x. All right. But what is it? This is equivalent to saying this is equivalent to that. So all I did was, here I should write an xn. Right, so all I'm using is that this f is just this function, and same here, f is just this function. But the right hand side I'll massage a little bit. So this is equivalent to saying, so yeah, I'll just use the fact that x is the limit of xn's and write it this way. Yeah, all I'm using is that x is this limit, but fk is a continuous function, so I can pull the limit out. So this would be equivalent to showing that. But now see what has happened. Let me color code. I hate this software. The limits have interchanged. So showing this is equivalent to showing that the limits can be interchanged. This limit has switched place with this limit. So this is the source of the obstruction or the problem. If we could interchange these limits, then yes, then we would be able to prove the continuity of f. And this shows that interchanging limits is a delicate business. Right? I mean, this shows that you cannot just interchange limits like that. It requires some additional hypothesis than just pointwise convergence. Okay, hopefully all of this made sense, and hopefully this motivates the next lecture, which will be about a stronger notion of convergence of a sequence of functions. Alright, so with that I want to end this lecture. As usual, like, comment, share, subscribe, and I will see you next time.